Okay, good morning everybody. Back again to photovoltaic and solar thermal. Today I will talk about thermal part. Okay, you remember we discussed the solar energy, the principles, the different collectors, the angle used to calculate the insulation approaching my collector, and then we started with the first type of collector, which is the photovoltaic, where we capture light, the photons, energy, and we produce electrical current. Now, let me start today with thermal collectors, and the next session this week, inshallah, we will talk about combined or hybrid system, what we call a thermal photovoltaic thermal system, PVT system. Now, you know that a huge amount of energy is coming from the sun. We discussed this, and this energy could be captured using different type of collector and for different type of applications, and we can use it to generate electricity, to heat water, to heat air, to let me say use it as a heating element in any industry required heating. Okay, now this energy, okay, uh, is, let me say, the soul of renewable energy. If we look to the International Energy Agency expectation or prediction up to 2040, we can see the trend is energy increase, trend is going up, all of them. Renewable energy is part of this, and the curves seem to be going up sharp, which means more focus on renewable energy. Solar energy is the soul of renewable energy. We expect, I mean, the IE actually expected, International Energy Agency expected that when we reach 2040, we will see that around, let me say, 30 to 40% of our energy consumption coming from renewable energy, and mainly solar energy, both parts, photovoltaic technology and thermal collectors. You may ask, okay, where can I use the solar thermal energy? What are applications? Applications, we have many. We can cool water, as example, in swimming pool. We use it for domestic heating, water heating. We use it for ventilation and heating inside building and houses, in let me say industrial process, and in generating electricity. Now, one of the application well known for people, which is solar water heater. You know, in Oman, as example, we use electrical heater. Okay, we heat the water using electricity. There is heater inside tank. Electricity follow, then heat I square R, which is heat at the end. We heat the water. We use it for shower or for let me say dishes, washing dishes or clothes, and so. But if we look to Europe, they don't have enough solar energy. However, they still use solar water heater. Why they don't go to electrical water? Because it's cheaper. Not only because of the environment and no, because it's cheaper. Even in some Arab countries to the north, as example, Lebanon, Palestine, Egypt, and other countries there, Jordan, actually they use solar water heater more because electricity is costly today, because of the part of the subsidy has been removed. The electricity become costly bit, so people will start thinking to have solar water heater. I will talk about it as example of how we use thermal energy coming from the sun. Okay, and we need to consider the thermodynamic, let me say, quantities, as example, heat flow, temperature, heat capacity, and so on. We already started the semester with one example. When you remember, when we heated, let me say, 1 liter of water using different type of technology, gas stove, let me say, electrical heater, coal, let me say, heater, and so on. So let me talk about this particular part. And by the way, the water heater in general, if it is electrical, if it is solar, is designed based on the number of person to be used by. As example, there is some collector, solar water, electrical water heater, the tanks, okay, can be used up to 6 persons, up to 10 persons. It's related to the number of persons are going to use this water heater. As example, in this building, the Barka building, engineering building, when we started the university, when they started going up with the building, we've been consulted, the lecturer at that time, we was in the old campus. We've been consulted about our opinion. One of each people, I mean, gave their opinion about their labs, and so for me, I advise is to use water heater. And now they are using in this building. There is no electrical water heater. There is only one solar water heater for the whole building applications. Now, heat, if you remember, we mentioned to the heat at the beginning in the example of when we heated water. So heat, which is change with respect to temperature, right, equal heat capacity C and M by M, which is the mass of the used fluid. And since C is constant, but M and delta theta, the temperature, it could be delta T or delta theta, it doesn't matter here because only the units will change. What happened is these are the variables, delta theta and M. So if we want to find the heat flow, okay, heat flow Q naught, okay, which is the differentiation of heat with respect to time, then it's two variables, then constant, which is C, we keep it constant all the time, differentiate the first, keeping the second constant, and differentiation the second, keeping the first constant, and we can find the heat flow through the fluid. Because at the end, if it is air, if it is water, or any other type of fluid, we want to know how it look like the heat flow through this fluid at the beginning. As example, if I have pipe, okay, the water will come cold through flowing through the pipe. When it flow through the pipe, it gets heated because the pipe is hot because it's capture energy. Definitely, it's worth mentioning that heat capacity is different from material to material. Here at this table, as you can see, heat capacity for different material, aluminium, copper, water, air, and so on. Now, when we have, let me say, a conductor conducting the fluid itself. As example, pipe conducting current, water current, or let me say a well when they do buildings. Okay, the well, the size of the well itself. Okay, how they can find they have different layers definitely. How they can find the heat flow? Have a look. Example. If I have pipe, okay, the pipe here, the parts of the pipe, the cylinder itself have layers. How the heat flow through this layer from outside to inside? Because as example, the solar radiation come here to heat the outside surface, and this outside surface will go, the temperature go inside, and when water flow here, it get heated. If it is air, it get heated. Okay. They use something close to the previous equation. This is delta theta, the temperature difference. This is the area of the surface, okay? And K is the constant. K is the coefficient of heat transfer, which is represented by this formula, as you can see here. They can use it to calculate the heat because this constant need to be substituted to find the heat flow. This constant is related to alpha, S, and lambda, where alpha, as you can see here, represent the surface coefficient. We have different surface, by the way, different layers, so different surface of heat transfer. Look to the material used, and then you can specify it, okay? And lambda thermal conductivity. For each material, there is specific lambda. As example, in this table, as you can see here, for steel, iron, and other type of material, each one of them have its thermal conductivity, its ability to conduct heat. As example, when we talk about, well, in a house, in our houses, outside our houses, the temperature is high. Inside, we want it cold. Okay? If we didn't consider this, and most people, they don't consider this, okay? The heat from out will go through the layer, through the wall inside, which means we need more cooling, which means we need more energy, which means we pay more money, right? But if we consider this, using insulator, design using different, let me say, materials, okay, there is a lot to be say here. Usually in the past, when I talked to civil engineering, I told them about this. I mean, how they select their material, and I will mention for this in energy conservation at the end of this semester. Also, S is the layer thickness. Okay, we need to know, as example, if this is the wall from here to here, temperature output here and temperature input here. This is my well, okay, it's contained different layers. From here to here is the total, let me say, thickness. For each layer there is thickness, okay, and heat, let me say, thermal conductivity. We need to consider this when we do calculation. Our students, talking about more than 10 years back, they designed solar water heater. This is how one of the systems they designed it. It's a very simple box from sheets. Inside there are pipes from copper. They painted, they are connected to each other. They are painting them with black to capture more energy, solar energy, and water coming from here. It come cold, it go out hot, warm. We can save it in a tank, okay? They did measurement for 1 day from 9:15 morning until 17:15 afternoon, okay? Or evening, let me say. You can see here two graphs. First graph, this one, the dotted one, is the in water, water coming from here, input. It's temperature. And the red one here is water out, inlet and outlet, okay? It seemed to be that it gets heated. The water here get heated when it's go through these pipes. It's going this way, and these pipes are hot now because they capture energy until it get out. And they try to do techno-economical assessment. It means they analyze it and assess the system technically after they design it and economically. And this, I just want to give an idea about how this system is important and is beneficial for people. And they're supposed to be used here. They're supposed to be used here in Oman. Okay, let's talk the two cases. The two cases here, EWH, which is electrical water heater for 6 people or for 4 people. And they calculate up to 10 years the annual cost. There is formula, they can use it to calculate the annual cost. Here at year number 1 is the capital cost, the money paid at the beginning to buy the electrical water heater. With time, this cost get increased. Why? Because we are paying for electricity every year. It get increased. When we reach after 10 years, we may see that it get increased sharply, okay, and there is amount added yearly, actually monthly, and then yearly, and this is how to calculate the cost. They say, okay, this system is designed for 6 persons, okay, let's compare both of them. We can see here in the other graph, okay, for the same 10 years, the same figure here for 6 persons, we copy it here, but this is here is the solar water heater, okay, system. Now, at the beginning, we pay more than electrical water heater. Yeah, the electrical water heater is cheaper. We pay more for solar water heater. But with time, as you can see here, after year number 2, 3, 4, at 4, because we are paying for electricity. For solar water heater, we'll not pay any more. We just pay when buy it. It do not need to pay for the fuel, maintenance, nothing. And because here we are paying for electricity, they are going to intersect here, which means they reach the same cost. After year number 4, this is for weather in Oman, they found that electrical water heater become more costly. You see here. For that, it's promising to use this type of system in Oman. They did calculations when they designed. Our students did calculation. As example here, they assume that they have water in 1,000 kilogram per liter. The volume and the diameter of the pipes used. They use pipes, okay? Their diameter, their length, the number of pipes inside the collector, and the heat capacity of the water itself. They want to find how much energy can be produced by this system. Okay, cylinder, they come to find the volume, okay, because based on the volume, we know how much water will be there. The volume of the cylinder is the area of the circle length and how many the number of pipes we use. They multiply it, and then they multiply the volume just calculated by the density, which is given in the question, to find the mass. They got it. And then temperature, when they measure, they try to apply this for only one instant of, let me say, one moment of when the temperature reach the highest or the maximum value, which is 92, comparing with late temperature at the beginning, and they substitute our formula. And this is the amount of energy, which is look like a huge amount of energy can be produced by one system. Imagine this is applied in every house. Many countries are applying this. This technology is not new. It's all technology talking about more than 60 years back. People are using this technology everywhere in the world. But here, the countries which is warm, hot countries, I'm talking about GCC countries, the 6 countries, and still they are using electrical water heater rather than they using solar water. Why? Because electricity is cheap, but now with time it gets expensive. Now, application of solar thermal collector and solar thermal energy, we can classify the application into based on the temperature itself. I mean, we classify the low, which is up to 100 Celsius, from 100 to 150 is the medium, from 150 to and above is the, let me say, the large or the high temperature applications. For 100, we can see it can be used solar dryer, hot water, cooking. For medium, we can use it for refrigeration, industrial heating, and above 150, definitely for generating electricity. These are two graphs here to show you their application based on the temperature. This is if we deal with water, and this is if we deal with air to heat them. Let's come here to the water. One of them is enough to be discussed here. You see, for a small temperature, it's heating swimming pools. And by the way, swimming pools, it is maybe not part of our culture here in the region that every house should have, but in some countries it's a must. People, they should have swimming pool in their houses, and for cold places they need to heat it in winter. So what they do? Using gas for heating or using electricity for heating is costly, but using solar energy is more cheaper. Okay, in this range between, let me say, 55 here up to 55 domestic space, more than domestic hot water, more than this we have a process in industry and so on. So it's look like it's related to the application itself and the temperature related to this application or that application. Now, we discussed the photovoltaic before, and for photovoltaic, what happened is we only deal with part of the spectrum, talking about the visual part, okay? But here we are dealing with most of the spectrum, even the infrared radiation and below, okay? So most of the spectrum are used here. Besides, you remember in photovoltaic, we talk about the efficiency. It's low in what's available now today in the market, less than 20, okay? But when you go to the solar thermal, we can see that we have high let me say, efficiency approaching, let me say, around between 50 to 80 now, okay? Now, what are the different solar systems, solar thermal systems? This photo from the history of people, they use lenses here. The temperature, use it to destroy the enemy ships, okay? You can find it in the historical, let me say, books. So it tells you that people are focusing the light and use it as a weapon here, okay? We can use this concentration in what we call it CSP, concentrated solar power. They concentrate the light, okay, and try to heat something, either fluid, either air, whatever it is. 3 systems are using here, main system for concentrating solar system. The central receiver and the parabolic dish and parabolic trough. Let me give a brief on each one of them, okay? Let me give a brief. Have a look. You see this one? This is dish type. This one is dish type. This is dish, similar to the dish we use it in our satellite at home for the TV, to watch TV. And this is the receiver. Our students designed similar to this one I will show you later on, okay? And it can produce energy up to supply, let me say, village, small village. Okay, one of them up to supply small village. And we have the central receiver, this one, receiver, okay, on a tower, and mirror surrounding it. You see here as example this one here, tower. You see here, this is the tower and this is the receiver, mirror surrounding it. When sun coming from this side or from this side or from this side, from any side, some mirror will focus the light on this tower. By the way, this system in California, it's working since 70 decades. Okay, 1970, after that, I mean, this power plant is working in California. So people are using these systems long time back. Okay, and these are the dishes, as I mentioned. This is the trough. The trough here, actually, we have two different types. One of them, the normal one, which is trough here, you can see here. It uses material which can reflect the solar radiation, the energy. As example, aluminium, or they coated with some type of material or mirror, whatever it is. But here the pipe, as you can see, the red pipe here, water, cold water coming here. When it goes through the pipe and the light focus on this pipe, which get heated, the water will be heated and produce steam, and they can use it in turbo generator to generate electricity. Sometimes they use another reflector. Okay. By the way, this system is the one used in North Oman, in Al Mazyuna. Okay, it's 1024 megawatt. It is the highest rating or capacity trough system, solar trough system in the world. Okay, it's used for oil enhancement recovery applications, collaboration between Glass Point, the American company, with PDO. Now, as I mentioned, we use solar thermal energy for heating, for cooling. Is it? Yeah. And for many other applications. Now, let me talk about two types of solar water heater, the flat plate and the evacuated tube. Flat plate, we can also classify it into passive and active. You know, active is always when we hear active, we understand that this is a smart one. Yes, correct. It's contains sensor, pumps, and so on. But for passive one, see, this is very simple diagram here to show you how it works. Have a look. This one is the tank in a box. I will take it here to explain it. This is box, as you can see here, isolated to contaminate the energy inside, and there is tank inside. This is the tank, and glass to cover the tank, to contaminate the heat inside, and cold water going from below. Okay, because usually the cold water is heavy, stay there, and the heat coming here, heat the pipe, the tank, and the hot water will be low in weight. It go up and then it can be used, or it can be taken to another storage, let me say tank, and to be used later, similar to the one we have here, but the one here is a smart one, or let me say active one. And they use usually, rather than we use pump here to make our system very simple, they use what they call it thermosiphon process. And you study this in secondary school. Thermosiphon process, what they do, they make the collector below the tank. So as you can see here, this is the collector and this is the tank. Water, cold water coming from here. It gets heated, so it go up, to rotate by nature. Okay, there is force and there is natural convection. Here is the natural convection. So the hot water coming up, and it will go with the cold. Cold will be part below, hot will be here, and then it can be taken to another pump and another tank to be stored there to be used in one way or another. You see here, this is real one in one country. Tank is there and the collector below. And by the way, when we say below, it doesn't mean that it should be very high difference or between them. No, a little centimeters. The height between them is a little centimeters, some. And if we use passive, active, then we use controller, we use pump, sensor, okay? So it become active. Now we don't need to put the collector below the tank. We can put it over the tank. Why? Because thermosiphon will not work here. Now the pump will work here. The pump will rotate the water, the warm water, the cold water, and warm water, both of them through the system. Okay. Now, in some cases, they use heat exchanger. Okay, heat exchanger. I will talk about these cases in the next slides. But heat exchanger for electrical, they didn't deal before. Chemical, they already deal with heat exchanger. It's like their transformer, okay? Our transformer, electrical people, I'm talking to you now. Our transformer is this transformer, right? Electrical current coming from here, going from here. There is no direct contact between these coils and energy transfer through electromagnetic fields from here to here. Something similar in heat exchanger for people dealing with thermal. Talking about mechanical, chemical, civil people, okay? They put it also here, two coils, but not conductor here, because they are not looking to the electrical current. No, they are looking to the water as example, current or water flow or any fluid. The water as example, hot coming here, by this is impressed in a material as example, it could be impressed in also water or another fluid. So this coil will give the heat to the medium here, okay, medium here, which is could be PCM, it could be water or any other fluid, and this coil will take from the medium there the heat and take it out, okay. So this is what happened. They use heat exchanger, and this tell me that we have two different, let me say, fluid here, one in one side of the heat exchanger and one in the other side of heat exchanger. Where they use it, have a look. If we are talking about rarely freezing in cold places, we can use the direct one. It's easy and direct. But when we have freezing temperature going to zero and plus minus, okay, then we have to use heat exchanger. Why? Because if the water get freeze, okay, become ice, it will not rotate, okay. But we can use another fluid rather than water, which can be freeze only in very cold or very low temperature. So make sure that it will not be freeze. This is what we call it indirect circulation system. And other system, sorry, which is a drain down system, what they do, they use a hybrid system. They use electric valve or electrical, let me say, heater to heat the water when it gets freeze, okay. When this is the low temperature below zero, it may reach 10-20 Celsius below zero. And the same thing actually happened in their vehicles. In their vehicles, you know, the petrol get freeze there, okay. It's cold, as example, North Europe, Canada, okay. So what they do, there is heater there inside the tank. It gets heating the fluid to fuel, sorry, to make it fluid. Now, this is one of the application in Europe. In many countries, they are using solar water heater with either direct or hybrid, sorry, they use with electrical heater, or they use heat exchanger. As you can see here, this is the heat exchanger. This is one coil, this is the other coil, and inside there is a fluid, and they transfer through heat through the fluid. The pipes of the collector, it can take different design. I will talk about them in the next slide, but these are the main or the well-known one, which this one is direct, let me say, in this way, and this is the parallel. Okay, water coming from here, going from here, or this is the parallel, water coming from here in parallel to all these pipes and then going from here outside. I will talk about them in the design. But I try to take here some photos from for some houses in Europe, and you can see here people, actually people, it is difficult to see house without having something related to solar on the roof, on their roof, because it is really interesting technology, cheap, and support their, let me say, energy needs. The second type of solar water heater is the evacuated tube. Evacuated tube is more used than the previous one because its efficiency is high, its energy produced is high, okay? The idea, how it look like this. You see here pipes, like pipe tubes, okay, tubes. Now, let me take one of them. It's look like from a glass tube, from a glass cylinder one, and pipes connected to fins. These are the fins, okay, to capture more energy. Now, for the glass to contaminate the energy, and the fins will collect the energy from any direction sun coming. The sun coming from any direction, it will capture this energy. These pipes, you can see there is pipe inside pipe. Now water will coming from the internal pipe and go at the end from the external pipe, so it get heated. They put them on the roof, as you can see here, or they can put them in park shadow to make park shadow for vehicles. And so you see here, each one of these represent evacuated tube. Now this is the evacuated tube. You can see here, this is the glass, this is the fins, and these are the pipes, the two pipes. You see here a comparison between, this is the temperature of the environment, this is if we use a flat plate, and this is if we use evacuated tube. It seems to be the temperature going up in evacuated tube, higher. Okay, you see the cold water coming here, red, okay, inside here, and the end going here from the external, taken to a tank or to use in one way or another. There is another type of evacuated tube, which is called U-pipe collector. U-pipe collector, similar to the previous one. Also, you can see it's a glass here. It's a glass. The fins will be now surrounding the pipes, and two pipes in the shape of U. In this way, you can see here, cold water coming from here is going out here to be heated. As I mentioned, we can use it also not only for heating water to produce hot water for small or medium application, also to generate electricity. This one, as I mentioned, trough system. This one trough system, similar to the one used in Oman. Now, this is the pipe, the collector, and light concentrated, sun energy concentrated on this pipe and get heated, or to generate electricity. Now we're generating electricity in this type of systems. Or we can use it for ventilation, heating homes, especially in the cold places. You can see this is the wall. It gets painted by black, here glass to make, let me say, gap between the wall and the glass. Energy captured, get heated, air get heated and taken by fan into internal room. This is the first project for PDO with the glass point. I remember 50 mega, and then later on they start with Mir'at 2 in the south of Oman, which is 1024 mega. It's approximately 1 giga. It's equivalent to one nuclear power plant. Now our students design system. This is more than 10 years back. Okay, these are our students at that time. They graduated. This is different type of system, different type of design. Okay, you see this is the collector, this is the tank, or another storage tank. Okay, some of our students, they design CSP, concentrated solar power. You see the mirrors, they brought dish and mirrors, and they use different type of receiver here, and they take the measurement to see how it perform. Some of them, they use also solar thermal system to for desalination. I mean, as example, they got the salty water here from the sea, and then try to use concentrator here to produce fresh water. Definitely coker, I don't need to talk about it, to cook foods. Now these systems, actually, what happened, one second, what happened for these systems is you can see this data is all data, okay? All data, talking about 2008. See China, United States, Germany. See the installed capacity of megawatt thermal. This is megawatt thermal. This means that this is hot, or let me say thermal energy coming from the sun. You see around 15 giga. 15,000 means 15 giga. But regardless the classification from what type of thermal they are using here, system. But see, we are talking about a huge amount of energy used by these countries from the solar energy. Example of classifying these parts, we can see they use 32% flat plate, air collector, and glass, and evacuated. Most of the system used today is evacuated because it is more effective, more efficient. I mentioned to the collector. Collector could have different design. You see here, there is direct flow, serpentine, parallel, modified. This is A, this is B, this is C. These are A, B, C. You can see different type of collector. The design of collector is part of how much we specify the energy to be captured. Okay, different design. Until today, researchers are producing more new, let me say, design. Recently, I published a new article in Elsevier in one of the journal related in the field, which is thermal science and engineering progress. I proposed a new design, and I manufactured it here in Sohar in university, and I did the calculation and the measurement, and we got interesting, let me say, results. It's hybrid system called using serpentine and direct, spiral and direct flow collector. Also, beside heating water, producing steam to generate electricity, we can use it for drying systems. Okay, solar drying system. This is designed for one of my PhD students graduating long time back. Okay, you can see this is the collector. Okay, by the way, you may say, okay, what are the application drying food, anything, fruits, fishes, meats, whatever they are. Okay, so cold air coming from here, and this is collector from meter glass on the top, and solar energy coming from here, it get heated, and then we can pull it using blower into chamber, and we put the food here, if it is dates or if it is fish. Okay, rather than, as example for this, rather than take 21 days to get dried, they can do it in a couple of hours, maybe, let me say 5, 6, 7 hours. So they reduce the time sorry, required for drying. Also fish, kasha, you call it kasha, right? I didn't try it yet. 20 years in Oman and didn't try it. For this is another application. Another one is solar cooking. How we can use solar energy to cook, sorry, to cool, let me say, rooms, buildings, and so. This is one of the systems. I just show you here how it look like the system. When I look at it, it seems to be similar to any electrical solar system. Okay, how the system work? You might say, just a minute, I have heat. How can I, from heat, I can produce cooling? Very simple. Let me first explain to you the process of how the air conditioning, electrical air conditioning work at home. What we have is a compressor pumping the gas. Sorry, pumping the gas, and it required huge amount of energy, because if the electricity here in Oman 230 volt, it's around, let me say simply 10, if not more, ampere, 10 ampere. When I multiply it, it's around 2300 watt. This is approximate. Okay, let's assume just multiply without looking to the cosine phi, which is the power factor. Now, when the compressor rotating the gas inside pipes, the gas affect the pipes and get cooled. The gas will make the pipe cooled. And these are the pipes. Okay, I put here fan in this way, blowing air going to these pipes, which is cold, and going from the other side, cold air. Very simple system. Now what they do, they say, okay, let's mix the gas with the fluid together, make them as a fluid, like water, similar to water. Okay, now what they do, rather than we use compressor, we use water pump. Its energy consumption is very low. As example, we may need, let me say, 0.2, okay, or let me say 0.5 ampere. If I multiply it by 230, okay, 115 watt. See how much energy I use in the first and second system. Here the system energy is very low. 115 is around one bulb, 100 watt, right? But just a minute, how this work? When I mix the gas with the water, we use what we call thermal driven air conditioning. How this work? Have a look. I collect the thermal energy. When I rotate the water, I need to separate again the gas from the water, okay, because I need the gas. So how we can separate it? Using thermal energy. When I separate it, the gas will follow through the pipes and blower here, and fan will blow the air, and then we got cold water. So thermal energy used for separation. Is this system available in Oman? Yeah, it's available, and many people are using. We didn't hear about this before. This is the point. Because people are not interested in renewable energy in this region, because this region is fossil fuel energy region. 1/3 of oil going to the world coming from this region. Oil and gas. There is oil and gas, both of them. For that, people are looking to oil and gas as the main source of energy. For that, they didn't look to other alternative. Other countries, they don't have, let me say, oil, they don't have gas. They look to this opportunity. Now, the applications, before I go to the applications and environment, have a look, ENGG. You may first time hear about ENGG. I don't know if chemical they deal with ENGG, but simply ENGG is another way to look to the thermal process. I will read the definition and explain it. ENGG is defined as the maximum amount of work, we're talking about here, that can be produced by system or a flow of matter or energy to reach equilibrium with a reference equivalent environment. Now what happens is we do ENGG analysis because we are dealing with energy, the flow of this energy in the system. If it is pipes, if it is surface, whatever it is, we need to analyze it to see where is the maximum energy flow, where is the minimum, where is the leak. This will give more insight into energy distribution on the surface on, let me say, pipes. It could be applied for thermal, and it could be applied for electrical, for, let me say, so they call it electrical ENGG and thermal ENGG. As I mentioned, application for this system are many. We can see they are in domestic application. I don't need to read, you can read from here. These are samples, commercial, industrial, okay, there are many applications. And definitely this will affect also the environment because we are not burning any fuel here. I will stop with this part, but before I take your questions, just in case, I would like to share with you